This is lecture 4A and the first lecture for our fourth unit of the semester. In our first unit, we learned about the structure of atoms. In our second unit, we learned how atoms bonded together. In our third unit, we learned about the properties of solids and liquids and solutions. And now finally, in our fourth unit, we're going to learn about how chemicals, atoms or molecules, react together. In order to represent a chemical reaction, we write what's called a chemical equation. That's just a representation of a chemical reaction using the elemental symbols and chemical formulas. An example would be something like this: CH4 plus O2 yields CO2 plus H2O. Anything written on the left side of the arrow, those are called the reactants. Anything written on the right side are called the products. That's what's created in the reaction. And the arrow is always read as yields. Now, if you have a proper chemical equation written, what has to be true is the number of atoms of each element on the reactant side have to exactly equal the number of atoms of each element on the product side. That's because in a chemical reaction, atoms are neither created nor destroyed. So if we're going to start with one carbon atom from the methane molecule CH4, we've got to end up with one carbon atom on the product side. If we start with 4 hydrogen atoms from the methane molecule on the reactant side, we have to end up with 4 hydrogen atoms in the water on the product side. Now, right now, the equation is not correct because we have 4 hydrogen atoms on the reactant side and only 2 hydrogen atoms on the right side. In order to remedy this situation, we do what's called balancing the equation. And the way we balance the equation is we adjust the coefficients in front of each reactant and product in order to equalize the number of atoms of each element. If we have 4 hydrogen atoms here on the reactant side and we want 4 hydrogen atoms here on the product side, you actually have 2 choices to fix that. You can change the formula of water to H4O, and that would balance the hydrogens. But water is not H4O, so we never actually change the formula of a compound. The way we balance the element hydrogen is we adjust how many water molecules are created during the chemical reaction. So we would stick a 2 in front of the H2O, and when you multiply 2 by 2, you get 4 hydrogens. So with that 2 there, this is now saying 1 carbon atom is turning into 1 carbon atom, 4 hydrogen atoms to start. We're ending with 4 hydrogen atoms. Now for the oxygens, I'm starting with 2 oxygen atoms, and I'm ending up with 2 in the carbon dioxide and 2 in the water. 2 plus 2 is 4. So I can't have 2 oxygen atoms changing into 4. I need more oxygens on the reactant side. I put a 2 in front of the O2. This is the process of balancing the equation. Now, additional information can be given in a chemical reaction. You can tell whether the reactants and products are solids, liquids, or gases by using a little symbol after each reactant or product. If a substance is a solid in a chemical reaction, we put a little S in parentheses after it. If something's a liquid, we put a little L in parentheses after it. If it's a gas, we put a G in parentheses. One other state which is common in chemical reactions is a material may be dissolved in water. If it is, we don't call it a liquid. A liquid means a pure material. If something's dissolved in water, it means it's mixed with water, and we use a different symbol to represent that. Any material dissolved in water is expressed as AQ for aqueous solution, which means a water solution. So here's an example of a reaction written with phases. This is the reaction between sodium and water, turning into sodium hydroxide and hydrogen gas. And the phases have been highlighted in orangish yellow here. This just helps you to visualize what's going on. A solid piece of sodium is added to liquid water. It produces a dissolved product, sodium hydroxide, and then gaseous hydrogen is produced as well. Now, we're going to go through the different types of chemical reactions, and there's maybe 7 different types we're going to wind up learning. And the first couple of types are oxidation-reduction reactions. An oxidation-reduction reaction, and sometimes it's contracted together to the term redox. So an oxidation-reduction reaction or a redox reaction are any type of chemical reaction in which atoms gain and lose electrons. The name or the reason it's called oxidation reduction is the term oxidation means something is losing electrons. The term reduction means something's gaining electrons. So we're saying there are some chemical reactions where one element loses electrons, undergoes oxidation, and another element gains those electrons and is therefore undergoing reduction. These two processes have to happen in tandem. One way to remember the definition is if you picture a lion's name quite often is Leo, and if you just think about Leo says Gur, that is lose electrons oxidation, gain electrons reduction, and that's actually how I remember those two definitions. So let's start going through our types of reactions. The first type of reaction is an oxidation reduction reaction, and it's called a composition reaction. I'm going to give you the general form of a composition reaction. A plus B goes to AB. This can either stand for two elements, A and B, combining to form a compound, or it could be two small molecules, A and B, combining to form a larger molecule. And one type of composition reaction that occurs is if A and B are elements. And a reaction will occur if active elements are put together because they will react to form a compound. So if A and B are active, they will wind up reacting as a composition reaction. An example of that would be sodium metal is placed into a container of chlorine gas. Sodium is a very active metal, chlorine is a very active nonmetal, so they'll react with each other. We want to try to represent that with a chemical equation. So elemental sodium is written as Na, and elemental chlorine is written as Cl2. If we look at an example of what happens when we put these two together, then we'll see if we can write the chemical reaction after that.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
So if we want to represent this chemical reaction by a chemical equation, we need a way to represent elemental sodium and elemental chlorine, which are the starting points of the reaction or the reactants. That chunk of sodium metal they showed in the video is millions and millions of sodium atoms. We've learned that metallic materials are made up of metal atoms. And because there's millions and millions of sodium atoms, the smallest particle of that elemental sodium metal is a sodium atom. We're going to represent that as Na in our balanced equation. The gaseous chlorine that we saw in the flask at the beginning, the yellowish green chlorine gas, is millions and millions of diatomic chlorine molecules. So to represent those millions and millions of diatomic chlorine molecules, we write one of them. We write Cl2. Let's stop that. So here are the reactants, Na plus Cl2. So when they reacted with each other, they will form a compound. Technically, what's happening is the sodium atoms are losing an electron to a chlorine atom. It's undergoing oxidation. When it loses its outer shell electron, it turns into an ion that has a charge of +1. When the chlorine gains the electron, it's going to wind up having a charge of -1 as it achieves a noble gas configuration as well. And because the sodium ion is +1 and the chloride ion is -1, the formula of the compound has to be NaCl. So that's the product. That's the ionic compound created when elemental sodium and elemental chlorine react. Now the equation is imbalanced. I can't switch the formula of sodium chloride to NaCl2. That would balance it, but NaCl2 is not the right formula for the combination of a +1 sodium ion and a -1 chloride ion. So I balance it with a 2 in front. To balance the sodiums, I need to put a 2 in front of the sodium on the left side, and now our equation is balanced. Let's see if we can add the phases from what we saw in the video. We saw sodium metal was a solid. We saw chlorine was a gas. Although we couldn't see it, what was formed in the container was sodium chloride, And from your knowledge of ionic compounds, we know that because they have very strong ionic bonds, that they melt at very high temperatures. So at room temperature, we would expect an ionic compound to be a solid. So this is going to wind up being the balanced chemical equation for the reaction between elemental sodium and elemental chlorine. So elemental reactions or products are always evidence that a redox reaction is going to occur. If you see any elemental material in an equation, the only way it's going to react is if it gains or loses electrons. So you can identify an oxidation reduction reaction by looking just at the basic equation itself if you see there are some elemental substances in the equation. In this case, there's elemental sodium and elemental chlorine. This is not elemental sodium and elemental chlorine. That's a sodium ion and a chloride ion. So these were the evidences that this would be an oxidation reduction reaction. If I write it more explicitly with the charges so you can see what's happening, elemental sodium is made up of neutral atoms, so I can emphasize that by putting a little 0 up here, meaning those are neutral atoms. And then what's the sodium doing? It's turning into a positive ion in the ionic compound sodium chloride, so it's losing an electron to become more positive. We'll start recognizing that anytime the charge of a species goes up, in this case from 0 to +1, the increase in charge always means oxidation because you're losing a negative electron. That's why you're becoming more positive. For the chlorine, it's starting as neutral atoms. They happen to be bonded together as a diatomic molecule, but they're still two neutral atoms. And when they react, they're becoming negative ions. So their charge is going from 0 down to -1. That process is called reduction, and that's actually why it's called reduction. Some people are confused by that. They go, why is gaining an electron called reduction? Well, it's because the charge is being reduced. You go from 0 down to -1. That's the process of reduction. The second type of reaction we're going to learn, also an oxidation reduction reaction, is called a replacement reaction. And the general form for that is A plus BX yields AX plus B. A represents an element and BX represents a compound. So what's happening here is this element A is replacing element B in the compound. Kicks it out, A now bonds with X, and B is given off on its own. There's several types of replacement reactions that'll happen, but in every single one, you will notice two things. First, if a reaction is going to occur, the element as a reactant has to be more reactive than the one it's replacing. And second, if A is a metal, it's going to replace the metal in a compound. If A is a nonmetal, it's going to replace the nonmetal in a compound. That's because metals form positive ions. So if you have a positive ion in a compound you're going to replace, you've got to replace it with another positive ion. It's got to be a metal with a metal. If you're going to be replacing a nonmetal in a compound, nonmetals form negative ions, you have to replace a negative ion with a negative ion. So the first type of replacement reaction we're going to talk about is active metals reacting with ions of less active metals. And as an example, we're going to try to write a balanced chemical equation for the reaction between elemental calcium metal being added to a test tube with an iron 3 nitrate solution. So from those words, let's try to write our equation. Elemental calcium metal, that would be written as Ca because it's millions and millions of neutral atoms making up the calcium metal, added to a test tube of a solution of iron 3 nitrate. So iron 3 nitrate would be Fe, NO3 taken 3 times. This is an element with a compound. We would expect a replacement reaction. Technically, it's only going to be a replacement reaction as long as this metal is more reactive than iron. And from trends we've learned on the periodic table, the further a metal is to the left of the periodic table, the more reactive it is. And calcium's further to the left than iron is, so calcium is more reactive, so we would expect a reaction to take place. And whenever it's an element with a compound, you're going to expect that metal element to replace this metal ion in the solution. So calcium is going to kick the iron out and bond with nitrate. Now, to write the correct formula, you wouldn't write CaNO3 taken 3 times because you see 3 nitrates on the left side. You have to think about what kind of ion calcium would form. And it's in the second column on the periodic table, so it's going to form a positive 2 ion, which means when it bonds with nitrate ions that are -1, it has to be CaNO3 taken twice. The iron is kicked out, and you get elemental iron formed as a product. In this reaction, it's oxidation reduction because this is a calcium atom that has a charge of 0. It's turning into a calcium ion that has a charge of +2. It's lost electrons. Where did those electrons go? The electrons went to the iron 3 ion. They gained the electrons, and they always gain enough electrons so that the iron ions or the metal ions that are reacting turn into an elemental atom. Now let's balance the equation. I have one calcium on the left, one calcium on the right, and the fact that one's an atom and one's an ion doesn't matter. It's the number of calciums you have to balance, whether they're atoms or ions, so that's balance. There's one iron on the left, there's one iron on the right, that's balance, but we have 3 NO3s on this side and 2 NO3s on the other. And when you have a polyatomic ion existing on both sides of a chemical equation, you can treat the entire polyatomic ion as if it were an individual element. So I'm going to treat the nitrates as individual elements. So to balance 3 nitrates with 2 nitrates, I'm going to have to put a 3 here, and then I'm going to have to put a 2 here in front of the iron, because that would make 6 nitrates on both sides. So when you have a 3 on one side and a 2 on the other, you do a common multiple of 6. So I would need to put a 2 here to balance the nitrates. This would be 2 times 3 is 6. 3 times 2 is 6. And then once I've done that, because I had 3 calciums here on the right side, I need to put a 3 in front of the calcium on the left side. And I have 2 irons now on the left, so I'll need to put a 2 in front of the iron on the right, and that would balance your equation. To write the phases, elemental calcium was a solid. They said we added it to a solution of iron 3 nitrate, so that means aqueous. And now the products are going to be guesswork on our part to a small extent. Calcium nitrate is going to be created in that water in that test tube, and ionic compounds, as we've learned, tend to have high water solubilities, so we would probably expect that compound to stay dissolved in the water. The last product is elemental iron metal, and elemental iron metal is a solid, doesn't dissolve in water, and that would be the expected phase for that. This type of balanced equation we have written is called a molecular equation because everything's written as if it were bonded together. But sometimes that's not the case. And it's not the case when you have reactants and products that have the phase of aqueous, because there are some aqueous substances, there are some dissolved materials that when they dissolve, they dissociate or ionize into ions. Those are electrolytes. And these are both ionic compounds in this equation here, and we know ionic compounds are electrolytes. When they dissolve in water, they dissociate into ions. So this isn't really the most accurate chemical equation we can write for this reaction. A more accurate reaction would be to separate the iron 3 nitrate and the calcium nitrate into their constituent ions, because that's really how they exist in the dissolved state. So to write a more accurate equation, I'm going to leave the 3 calcium atoms exactly how they are, because that's how calcium metal is. It's millions and millions of calcium atoms. But the iron 3 nitrate isn't bonded together as a formula unit. Each iron 3 nitrate dissociates into 1 iron 3 ion and 3 nitrate ions. But because you have a 2 in the front, you're going to have to multiply each of those by 2 or distribute the 2. So if I multiply 2 times 1, that's going to make 2 iron ions. And if I multiply 2 times 3, that's going to make 6 nitrate ions. So we're going to actually have 2 iron 3 ions and 6 nitrate ions, and that's a more accurate way to write iron 3 nitrate when it's in its dissolved state. On the product side, we'll do the same thing with this soluble electrolyte. Calcium nitrate formula units dissociate into 1 calcium +2 ion and then 2 nitrate -1 ions. But with a 3 in the front, I'm going to distribute that. I'm going to actually have 3 calcium ions and then 6 nitrate ions. And now that's written more accurately. And then finally, when I get to my metallic material, metals exist as atoms, so I'm going to write it exactly how it is. That's showing iron existing as neutral atoms. If you've improved this equation by writing it more accurately, and we do that by ionizing or dissociating electrolytes, we call that an ionic equation. This is the ionic equation for the reaction between calcium metal and a solution of iron 3 nitrate. Now, if you look at this equation, you may notice that there are 6 nitrate ions on the reactant side and there's 6 nitrate ions on the product side. If anything's exactly the same on the reactant and product side, you can cancel those out because they're really not reacting. There are a bunch of nitrate ions in that solution, but they're not involved in the chemical change, just like there's millions and millions of water molecules in that test tube, but those water molecules aren't reacting. I'm not writing them in the equation. Now, I do have calcium on this side and calcium on this side, but this one's an atom, this one's an ion. Those aren't the same. They don't cancel out. And the same thing for the iron 3 and the iron. So the only identical species in this are the nitrate ions. We call those spectator ions because they're actually not undergoing any chemical change. And if you write what's left over after you cancel out the spectator ions, we have 3 calcium solid plus 2 iron 3 ions aqueous yields 3 calcium ions aqueous plus 2 iron atoms solid. And we call this, we call this the net ionic equation. And if you want to emphasize what's happening here, the calcium atoms have no charge and the iron atoms have no charge. Not necessary to do that, but I just want to point out this is just a way to emphasize it's an oxidation reduction reaction. The calcium atoms are going from a charge of 0 to a charge of positive 2. They're losing electrons. The iron 3 ions are going from a charge of positive 3 to a charge of 0. They're gaining electrons. And anytime you have an oxidation reduction reaction, whether it's a composition reaction or now a replacement reaction, we can write this reaction as the sum of these 2 different processes, oxidation and reduction. So this balanced net ionic equation that we've just produced can be written as an oxidation half reaction and a reduction half reaction, which if we added those together, they would yield the reaction we have written at the top of the slide here. So what's being oxidized? What's being oxidized is the element whose charge is going up. Calcium's charge is 0. Here it's positive 2. Going from 0 to positive 2 means going up. So the reaction of the 3 calcium atoms turning into the 3 calcium ions has to be oxidation. The reduction reaction would be the iron 3 ions turning into the iron atoms. Now, if I want to balance this oxidation half reaction, the first thing I need to do is I need to make sure the atoms of each element are balanced. And in my oxidation half reaction, I have 3 calcium atoms going to 3 calcium ions. The calciums are balanced. The second thing you need to do is you need to balance the charge, because right now we have 3 neutral atoms on the reactant side and 3 positive 2 ions on the product side. 3 times 2 means the charge of the products are 6. This side is 0, this side is 6. You can't have a correctly balanced equation in which a charge changes. That means electrons are either created or destroyed, and that's impossible. So the way you fix this is you balance the charge by adding electrons. And electrons are negative, so we're going to have to add 6 electrons to the product side so that when I add the 6 negative electron charges here with the 6 positive charges from the calciums, negative 6 and positive 6 is 0, and that exactly equals the charge on this side here. For the reduction half reaction, it's the 3 iron 3 ions turning into the 2 iron atoms. The charge is going from plus 3 down to 0. If the charge gets reduced, that's reduction. The ions are balanced, 2 on each side. To balance the charge, the overall charge on the reactant side is 2 times 3 is 6. The overall charge on the product side is 0. So I'm going to have to add 6 negative electrons to the reactant side so that negative 6 and positive 6 adds up to be 0. And both sides have a charge of 0 now. So now if we take these 2 half reactions, the oxidation and the reduction, if we were to add them together, you would notice you have 6 electrons on the right side here, 6 electrons on the left side there, and they would actually cancel out. So electrons lost and gained should be exactly equal. So now that if you add these 2 reactions together, the 6 electrons will cancel out, and you're going to get the exact reaction at the very top. So adding the 2 half reactions together produce the overall reaction. Any oxidation reduction reaction can always be broken down and written as the sum of an oxidation half reaction and a reduction half reaction. The second type of replacement reaction I want to talk about are active metals reacting with hydrogen ions in acids. And as an example for this, we're going to do the reaction of aluminum metal added to a solution of hydrochloric acid. This type of reaction occurs for all metals on the periodic table except for noble metals, coinage metals, and mercury. These are the only ones that are not active enough to react with the hydrogen ions that are found in acids. So aluminum is an example of a metal that is active enough. So that means a piece of aluminum metal should be able to react with hydrochloric acid. In this reaction, you can see the general form of a replacement reaction, element with a compound. So what's going to happen is the aluminum is going to replace the hydrogen, and it's going to wind up bonding with the chlorine. Why would it do that? Well, aluminum forms positive ions, and hydrogen's the positive component in hydrochloric acid. So positive has to replace a positive. So if the aluminum replaces the hydrogen, the aluminum will bond with the chloride. The aluminum ion created has a charge from its column on the periodic table of +3. So if it has a +3 charge, it would need to bond to 3 -1 chlorides. Its formula would be AlCl3. The hydrogen would be given off in its elemental form, and hydrogen is one of the nonmetals that in their elemental form pair up to form diatomic molecules. So the correct formula for elemental hydrogen would be H2. So these are the predicted products for this replacement reaction. The equation's not balanced how it's written. I have 1 aluminum and 1 aluminum on each side. That's fine. I have 1 hydrogen and 2 hydrogens. That's not fine. I have 3 chlorines and 1 chlorine. That's not fine. So 2 of the elements are not balanced. So if I want to balance the hydrogens, my 2 hydrogens here, I'll put a 2 there in front of the HCl to balance those. That now makes 2 chlorines on this side, but there's 3 chlorines on this side. And whenever you have a situation of 2 and 3, you've got to find a common multiple of 6. So that 2 I just wrote, I'm going to have to erase it. So sometimes that happens. Don't feel bad about that. Switch it to a 6. And then to balance the chlorines on the other side of the equation, I'm going to put a 2 here to give me 6 chlorines on the product side. So now the chlorines are balanced, but the hydrogens aren't. Now I have 6 on the left side. I only have 2 on the right. I'll need to put a 3 there. And then to balance the aluminums, I have 2 here. I'll put a 2 in front of the aluminum on the left side, and now we have a balanced equation. For the phases, elemental aluminum metal is a solid. It said we added aluminum metal to a solution of hydrochloric acid, so that means that's AQ. We're forming aluminum chloride, which is an ionic compound, and this is being formed in the water of the hydrochloric acid solution, and ionic compounds tend to be soluble in water, so most likely this would be aqueous. And then elemental hydrogen is a gaseous material. This is our balanced molecular equation. And because I have 2 components in this equation that are in a water solution, if these are strong electrolytes, that means this equation is not the most accurate I can write. HCl is a strong acid, which is a strong electrolyte, so that means this can be improved in how it's written. And then the aluminum chloride is a soluble ionic compound that dissociates into ions, so that can be written more correctly by having this aluminum chloride ions separate from each other. So we're going to now write this in ionic form. So aluminum metal is written correctly because aluminum metal is already made up of aluminum atoms. Don't stick a charge up here. Aluminum metal is made up of aluminum atoms. It's not made of aluminum ions. This is actually perfectly fine. It's the hydrochloric acid we need to fix because that's a strong acid, so it's a strong electrolyte. And each HCl, when you dissolve it in water, will ionize into a hydrogen ion and a chloride ion. With the 6 in front, you're going to distribute the 6 to each of those. So you're going to actually have 6 hydrogen ions and 6 chloride ions. And this is the more accurate way to represent the solution with hydrochloric acid. On the product side, we have the soluble ionic compound aluminum chloride. They dissociate in water. Each aluminum chloride formula unit dissociates into 1 aluminum +3 ion and 3 chloride ions. Because there's a 2 in front, I'm going to distribute the 2 to each of those. So 2 times 1 would make 2 aluminum +3 ions, and 2 times 3 makes 6 chloride -1 ions. This is written correctly now. These are charged species because this is an ionic compound. So make sure you see the difference here. I mean, it just says Al here, and it just says Al there, and it looks really similar, but you've got to see the context. This is elemental aluminum that's a solid. What are metals made of? Atoms. Atoms are neutral. This is an ionic compound. What are ionic compounds made of? They're made of ions. And so we write these as ions in the ionic equation. This is elemental hydrogen gas. Hydrogen gas exists as hydrogen atoms that happen to bond together in diatomic form. So you write them as 3H2. They do not separate into ions. This would be your ionic equation. And in this equation, if you notice, there's one thing that's the same on the reactant and product side. That's the 6 chloride ions here and the 6 chloride ions there. Those are spectator ions. So if you cancel those out, you'll have left over the net ionic equation, which will be 2 aluminum atoms solid plus 6 hydrogen ions aqueous yields 2 aluminum positive 3 ions aqueous plus 3 H2 molecules in the gaseous state. Oxidation reduction reaction, because the aluminum atoms are going from 0 up to positive 3. So if your oxidation number is going up, or your charge is going up rather, then that means you're being oxidized. So in this reaction, the aluminum is what's being oxidized. The hydrogens are going from a charge of +1 down to 0. If your charge is being reduced, you're undergoing reduction. So we would say the hydrogen ions are undergoing reduction in this particular reaction. Okay? If that makes sense, why don't you take a moment, see if you can write a proper balanced molecular ionic and net ionic equation for the reaction between silver metal added to a solution of hydrochloric acid. And then let's go ahead and try to do that now. A piece of silver metal will be written as Ag added to a solution of hydrochloric acid means plus HCl. Looks like a replacement reaction. You would have the silver replace the hydrogen, and you would form the compound AgCl +1 - 1, and hydrogen be given off as H2. But unfortunately, that's not correct, because a replacement reaction of a metal with an acid only happens if the metal is active enough. So it'll happen with all metals on the periodic table except the coinage metals, the noble metals, and mercury. And silver happens to be a coinage metal, so therefore it doesn't react. That's actually important. That's why we make money and jewelry out of things like silver and gold and platinum, because if we drop our silver ring or our gold coin into our salad dressing or into our orange juice, we don't want it to react away, and then we don't have it anymore. So anything that's of any value that's made out of metals, people make with unreactive metals like the coinage metals, platinum metals, or they wouldn't make it out of mercury, but mercury is another metal that's very unreactive. Okay. The third type of replacement reaction is a very active metals can react with hydrogen and water. So I've got the term very in here because you have to have a really reactive metal if it's going to react just with pure water. And the only metals that do this are the metals from the first column on the periodic table, which are the alkali metals, and then some of the bottom metals in the second column on the periodic table, calcium, strontium, barium, and then radium. So these are actually active enough that they will react with the hydrogen and water. And we saw this earlier in one of our experiments this semester. We took a piece of sodium metal, it was on a video, and we dropped that sodium metal into a glass of water. So let's see if we can write the balanced equation between the very active metal sodium and water. For you to be able to predict the product of this chemical reaction, whenever water is involved in a replacement reaction, you'll recognize that because what do we have here? Typical element with a compound. That would be a replacement. You have to think of water in a different way. Water actually behaves as if it were the ionic compound hydrogen hydroxide. So if you erase the water and write it hydrogen hydroxide, now you'll be able to predict the correct products of the replacement reaction. The sodium is going to replace the hydrogen because the hydrogen's the positive component now, and sodium will form positive ions. So if it replaces that hydrogen, sodium will turn into a +1 ion. First column on the periodic table always makes ions of +1, and it will bond with the hydroxide. And when it bonds with the hydroxide, it'll form NaOH. The hydrogen will be given off, and in its elemental form, it'll form diatomic molecules. So these would be the products in the chemical reaction. To balance this, I have 1 sodium on each side. And then what I would do is I would balance the hydroxides as their own unit. So here's a hydroxide, that's balanced. So the only thing that isn't balanced is the single hydrogen here with the 2 single hydrogens there. We'll need to put a 2 in front of the H2O here. That now makes 2 hydroxides on the left, so I'll need to put a 2 in front of the NaOH to balance those. And that now makes 2 sodiums on the right, so a 2 in front of the Na on the left. And now we have a balanced equation. For phases, elemental sodium is a solid metal. Water is a liquid. The sodium hydroxide is being produced in that water, and it's an ionic compound, and ionic compounds tend to have high water solubility, so we would guess that would be aqueous. And then hydrogen's winding up to be a gas. Okay? Now, we have something that's aqueous in this equation, so that means we can write this more accurately by taking that sodium hydroxide ionic compound and dissociate it into its constituent ions. So the elemental sodium is already written as atoms, that's fine. Water is a molecule. Water molecules do not ionize. Strong acids ionize. Water molecules don't. They exist in the molecular form. You can leave this 2 HOHs, or you can write it 2 H2O liquids. But it doesn't exist as hydrogen ions and hydroxide ions. You're not drinking a glass of billions of hydrogen ions and billions of hydroxides. You're drinking a molecular substance, H2Os. But on the product side, if you dissolve sodium hydroxide in water, that solution will have lots of sodium ions and lots of hydroxide ions, and I've multiplied by 2 because of the coefficient. The hydrogen gas exists as diatomic neutral atom molecules, so that's perfect. And then if you look for a spectator ion here, there are no spectator ions, so this ionic equation is also going to be the net ionic equation, so we're done with this one. The final type of replacement reaction is that active halogens reacting with ions of less active halogens. This is going to be a replacement of nonmetals. An example of this would be chlorine gas is bubbled into a solution of lithium bromide. So chlorine gas, Cl2, elemental form, bubbled into a solution of lithium bromide +1 -1 LiBr. Once again, it's an element with a compound, so it's going to be a replacement reaction. Each of the ones we've seen before, we've gotten used to replacing the first element because this has always been a substance that will create positive ions. But because chlorine will turn into a negative ion, it has to replace the negative component in the compound, so it replaces the bromide. So the chlorine is going to actually bond with the lithium, and lithium is +1, the chloride ion will be -1, that'll be LiCl, and the bromide ion turns into elemental bromine, which is a diatomic molecule, so it's given off in its elemental form, Br2. To balance the equation, we have 2 chlorines on the left, so we need 2 chlorines on the right, 2 in front of the LiCl. That makes 2 lithiums on the right side, so we'll put a 2 in front of the LiBr to balance that, and now the bromines are balanced 2 and 2. The phases for this, the chlorine is a gas. It said we bubbled it into a solution of lithium bromide, so a solution would be AQ. We're forming lithium chloride in that water solution, and ionic compounds have high water solubility, so that will probably be aqueous. And then we form elemental bromine, and if you notice from the periodic table, elemental bromine is one of the 2 elements that are liquids at room temperature, so you'd actually form liquid bromine. So this is our molecular equation for the reaction. Because we have a strong electrolyte here and a strong electrolyte here, this reaction can be written more accurately in ionic form. So the elemental chlorine exists as diatomic molecules, it's written fine, but the strong electrolyte really exists as separated ions, so I'm going to dissociate the lithium bromide into 2 lithium +1 ions and 2 bromide -1 ions. This is going to form lithium chloride, which is also a strong electrolyte, so that'll be dissociated in solution, 2 lithium ions plus 2 chloride ions. And then elemental bromine exists as diatomic molecules, so it's already written correctly. In this ionic equation, notice there are 2 lithium ions on the left and the right side that are identical. They will cancel out as the spectator ions, and our final net ionic equation will be the Cl2 gas plus 2 Br- aqueous yields 2 Cl- aqueous plus Br2 liquid. This is an oxidation reduction reaction. If I add the little zeros here for the elemental substances, the chlorines are going from 0 to -1. Their charges are going down. They're undergoing reduction. The bromides are going from -1 up to 0. They're undergoing oxidation. And if we want to try to write this reaction as an oxidation half reaction and a reduction half reaction, the bromide ions are turning into elemental bromine. So we balance the bromines 2 and 2. Now we have to balance the charge, and the charge on the left side is -2. The charge on the right side is 0. So you're going to balance the charge by adding electrons, and we can't add electrons to the left side. That would make the charge a bigger negative number. We need to put them on the right side, and we need 2 of them. So 2 electrons here would make the charge on the left and the right side both equal to -2. So notice when you balance charge, you don't have to make the charge on each side 0. They just have to be equal to each other. This is the oxidation half reaction because the bromide ions are going from -1 up to 0. If the charge gets higher, that means you're undergoing oxidation, and oxidation is losing electrons. You've lost the 2 electrons. The Br minuses have lost a pair of electrons. The other half reaction is the diatomic chlorine turning into 2 chloride ions. The chlorines are balanced. To balance the charge, I would need to add 2 negative electrons to the left side, and because this reaction is gaining electrons, or the charge of the chlorine is going from 0 down to -1, that's how we know that's the reduction half reaction. We've actually seen this reaction before. In one of our previous experiments, we actually took a solution that contained chlorine gas, and chlorine gas has a characteristic yellow color in heptane, and we added bromide to it, and we shook it up or put it in the vortex mixer. And when we did, the color in the heptane layer changed to orange. What did that mean? That means the chlorine reacted away, so it was no longer yellow, and we formed the orange color of the diatomic bromine. So that was an example of this particular replacement reaction. The final type of reaction we're going to talk about are combustion reactions. And a combustion reaction has a general form like this. A compound, I'll call AX, reacts with oxygen. And what happens is the oxygen, being so reactive, forms a compound with both element A and element X. So whenever you hear somebody saying combustion in air, or more commonly burning in air, that's a combustion reaction. And burning in air means something is reacting with oxygen. And when it reacts with oxygen, it forms oxide compounds of each element in the compound burned. Let's try an example of this. Let's say we take butane and we burn butane in air. Butane is a hydrocarbon, C4H10. So if butane is going to be burned in air, the reaction would be C4H10 plus O2. That's what burning means. Not the same as heating. If I say I heated up butane, I'm just warming it up. If I say I'm burning butane, that's what means reacts with oxygen. So what's going to happen is the oxygen is so reactive, the oxygen will form a compound with carbon, and the oxygen will form a compound with hydrogen. So you form 2 compounds, and you just have to think about what might be the most common compound between carbon and oxygen, and what might be the most common compound between oxygen and hydrogen. And between carbon and oxygen, that would be carbon dioxide. And between oxygen and hydrogen, that would be water. Those are your products. So anytime there's a butane is being burned in a butane stove or a lighter, then you're actually forming an oxide of carbon, which is CO2, and an oxide of hydrogen, which is H2O. This reaction just happens to be very exothermic, so it gives off a lot of heat, and it also gives off light. And that's what we usually associate with the idea of burning or combustion, heat and light being evolved. Let's balance the equation. We have 4 carbons on the left, so we need to put a 4 here to balance those. I have 10 hydrogens on the left, so to get 10 hydrogens on the right, I'll need to put a 5 here. Now watch the oxygens. 4 times 2 is 8. 5 times 1 is 5. 8 plus 5 is 13. I have 13 oxygens on the right, so to get 13 oxygens on the left, I would need to put, correct, 6.5. Well, there's a problem. You can't have half an oxygen molecule. So if you ever wind up having to balance equation with a fractional coefficient, what you do is whatever the denominator of the fraction is, multiply every coefficient by the denominator of that fraction. So if a fractional coefficient is needed, multiply every coefficient by that fraction's denominator. So I'm going to multiply this coefficient by the denominator of that fraction. So 1 times 2 is 2. Then I'm going to multiply the 6.5 by 2, and that's going to make it 13. Then I'm going to multiply the 4 by 2. That's going to make it 8. And then I'm going to multiply the 5 by 2, and that's going to make it 10. It's still going to be balanced. You just doubled the number of atoms, but now you don't have any fractions. For the phases, butane is actually a gas, oxygen is a gas, carbon dioxide is a gas, and water, which is normally a liquid, isn't a liquid now because when you burn something, the temperature is really, really high. It's above 100 degrees Celsius, so water is given off in the gaseous state. If that makes sense, let's try one more. Let's see if we can write the balanced equation for the burning of zinc sulfide. So zinc sulfide, zinc is plus 2 ions, sulfide's negative 2 ions. The formula would be ZnS. If zinc sulfide is burned, the reactants would be ZnS plus O2. So the products of a burning reaction are always oxides of each element in the compound. So oxygen is going to form a compound with zinc, and this can be easily determined because we know zinc ions are positive 2, oxide ions are always negative 2. It has to be the formula ZnO. But to come up with a compound between sulfur and oxygen, because these are nonmetals, you would just have to know what the most common oxide is of sulfur. And the most stable or most common oxide of sulfur is actually sulfur dioxide. So much like I think in the last problem, you sort of already knew that carbon forms carbon dioxide most stably and hydrogen forms water most stably, you will need to know that sulfur forms sulfur dioxide most stably. So you're going to get zinc oxide and sulfur dioxide. To balance this equation, 1 zinc, 1 zinc, 1 sulfur, 1 sulfur, and now we get to the oxygens. There are 3 oxygens here, but there's only 2 oxygens here. So to balance that, we're going to need to use a 1.5. Once again, it's a fractional coefficient. That gives us 3 oxygens on both sides of the equation. And to get rid of that fraction, we're going to multiply every coefficient by the denominator in that fraction, which is 2. So in front of the zinc sulfide, I'm going to multiply the 1 by 2. I'm going to multiply this by 2. I'm going to multiply this by 2. I'm going to multiply this by 2. And now we have our balanced equation. Zinc sulfide is an ionic compound. Ionic compounds have strong ionic bonds, high melting points. It's going to be a solid. It's not aqueous. We didn't try to burn a water solution of zinc sulfide. They said you try to burn solid zinc sulfide. So it's not aqueous unless it says the substance is dissolved in water. Oxygen's a gas. You're forming zinc oxide. That's an ionic compound, and ionic compounds have high melting points. They're going to be solids unless it's being formed in a water solution, but you're usually not burning things underwater, so I didn't hear any water in this one. And then sulfur dioxide is a gaseous substance.